sklearnsvmLinearSVC. Description: LinearSVC is a linear support vector machine classifier in scikit-learn. It implements a 1vs REST multi-class strategy, meaning it trains a separate linear model for each class, comparing it to all other classes. LinearSVC is efficient for large datasets and performs well when the data is linearly separable. Inputs: X a 2D array containing the training features. Each row represents a data point, and each column represents a feature. Y a 1D array containing the target labels for each data point in X. Outputs: the fitted linear SVC model, which can be used to predict labels for new data points. Core a 2D array containing the coefficients of the decision function. Each row corresponds to a class, and each column corresponds to a feature. Intercept a 1D array containing the intercept of the decision function for each class. Steps: the linear SVC algorithm learns a hyperplane in the feature space that maximizes the margin between the different classes. This hyperplane is defined by a set of coefficients and an intercept, which are learned during training. The model uses the learned hyperplane to classify new data points by determining which side of the hyperplane they fall on. Metrics: accuracy, the percentage of correctly classified data points. Precision, the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall, the proportion of correctly predicted positive instances out of all actual positive instances. F1 score, a harmonic mean of precision and recall, providing a balance between the two. Visualization plots: decision boundary plot, a plot showing the hyperplane learned by the model, along with the data points and their classifications. Feature importance plot, a plot showing the coefficients of the decision function, indicating the relative importance of each feature in the classification process. Fine-tune parameters: see the regularization parameter, controlling the trade-off between maximizing the margin and minimizing the training error. A higher C value leads to a smaller margin but lower training error. Penalty: the type of penalty used for regularization, either L1 or L2. L1 penalty encourages sparsity in the coefficients, while L2 penalty encourages smaller coefficients. Loss: the loss function used for optimization, either squared hinge or hinge. Squared hinge loss is more sensitive to outliers, while hinge loss is more robust. Dual: whether to use the dual formulation of the optimization problem. Dual formulation is more efficient for large datasets with many features, while primal formulation is more efficient for small datasets with few features. Toll: the tolerance for stopping the optimization algorithm. Uncertainty methods: confidence scores, the decision function output provides confidence scores for each class. Higher scores indicate higher confidence in the predicted class. Challenges and fixes: Challenge 1: overfitting. The model may overfit to the training data, resulting in poor generalization performance on unseen data. Sample use case: when the training data is very small or contains a lot of noise, the model may learn to fit the noise rather than the underlying patterns, leading to overfitting. Fixes to challenge 1: use regularization C parameter to penalize complex models and encourage simpler models that generalize better. Use cross-validation techniques to evaluate the model performance on unseen data and adjust the regularization parameter accordingly. Consider using data augmentation techniques to increase the size and diversity of the training data, reducing the risk of overfitting. Challenge 2: data scalability for very large datasets. The training time can be significant. Sample use case: when the number of features is very large or the dataset is very large, training can become computationally expensive. Fixes to challenge 2. Use techniques like stochastic gradient descent (SGD) to optimize the model more efficiently. Especially for large datasets, consider using feature selection techniques to reduce the number of features, which can speed up training and improve model performance. Explore using a different, potentially more efficient, machine learning algorithm for large datasets, such as a decision tree or random forest. Challenge 3. Nonlinear data. LinearSVC is designed for linearly separable data, so it may not perform well on datasets with complex, nonlinear relationships between features and target labels. Sample use case. If the data has a nonlinear decision boundary, the linear model may fail to separate the classes accurately. Fixes to challenge 3. Use a nonlinear kernel function within the support vector machine framework (SVC) to transform data into a higher dimensional space where it may be linearly separable. Consider using other nonlinear machine learning algorithms, such as decision trees or neural networks, which are better suited for handling nonlinear relationships.